Welcome to our journey through the mysteries of the universe. Today, we explore one of the most profound questions in science. What happened before the Big Bang, and how did our universe begin? For centuries, humans have gazed at the stars, wondering about our origins. The Big Bang Theory offers a compelling explanation for the birth of the cosmos, but what about the moments before? In this video, we'll dive into scientific theories, philosophical ideas, and the latest discoveries that shed light on the universe's earliest moments. Let's embark on this cosmic adventure together, starting with the basics of the Big Bang Theory. The Big Bang Theory is the prevailing cosmological model explaining the observable universe's origin. According to this theory, the universe began as a singularity, a point of infinite density and temperature about 13.8 billion years ago. From this singularity, space, time, and matter expanded rapidly, creating everything we see today. Scientists have gathered evidence for the Big Bang through observations of cosmic microwave background radiation, the abundance of light elements, and the expansion of galaxies. But what exactly is a singularity, and why did the universe start expanding? Let's explore these questions in the next scene. A singularity is a point where physical quantities like density and temperature become infinite. In the context of the Big Bang, it represents the starting point of our universe. However, the concept of a singularity is more of a mathematical abstraction than a physical reality. Our current laws of physics break down at this point, making it difficult to describe what actually happened. This mystery has led scientists to search for a theory that can unify quantum mechanics and general relativity, potentially revealing what occurred at the universe's birth. Next, we'll look at the evidence supporting the Big Bang theory. One of the strongest pieces of evidence for the Big Bang is the cosmic microwave background, CMB. This faint glow permeates the entire universe and is a remnant of the early, hot, dense state. Discovered in 1965, the CMB provides a snapshot of the universe about 380,000 years after the Big Bang, when atoms first formed and light could travel freely. The uniformity and slight variations in the CMB have helped scientists understand the universe's structure and evolution. Next, we'll discuss the expansion of the universe and what it tells us about its beginnings. Another key piece of evidence is the expansion of the universe. In 1929, Edwin Hubble observed that galaxies are moving away from us, indicating that the universe is expanding. This discovery supports the idea that the universe began from a hot, dense state and has been growing ever since. The rate of expansion, known as the Hubble constant, helps scientists estimate the age of the universe. But what caused this expansion, and what does it mean for the universe's origin? Let's delve into the concept of cosmic inflation in the next scene. Cosmic inflation is a theory that explains the rapid expansion of the universe in its earliest moments. Proposed by Alan Guth in the 1980s, inflation suggests that the universe expanded exponentially within a fraction of a second after the Big Bang. This process smoothed out any irregularities and set the stage for the formation of galaxies and other structures. Inflation also explains the uniformity of the cosmic microwave background and the distribution of matter in the universe. But what triggered inflation, and what existed before it? Let's explore these questions next. The period before cosmic inflation remains one of the greatest mysteries in cosmology. Our current theories cannot describe what happened before this rapid expansion. Some scientists propose that quantum fluctuations in a vacuum could have triggered inflation, while others suggest the existence of a multiverse or other dimensions. The lack of observational evidence makes it difficult to test these ideas. Nevertheless, researchers continue to explore new models and seek clues in the cosmic microwave background and other phenomena. Next, we'll look at quantum mechanics and its role in the universe's origin. Quantum mechanics is the branch of physics that describes the behavior of particles at the smallest scales. In the context of the universe's origin, quantum mechanics suggests that the universe could have emerged from a quantum fluctuation. This idea challenges our classical understanding of cause and effect, allowing for the possibility that the universe appeared spontaneously. Quantum mechanics also plays a crucial role in attempts to unify gravity and other forces, which may help explain what happened before the Big Bang. Let's explore the concept of quantum fluctuations next. Quantum fluctuations are temporary changes in energy that occur in empty space due to the uncertainty principle. These fluctuations can create particles and antiparticles that exist for brief moments before annihilating each other. Some theories suggest that a quantum fluctuation could have sparked the birth of our universe, leading to the Big Bang. This concept is difficult to test, but it provides a possible explanation for how something could arise from nothing. Next, we'll discuss the idea of the multiverse and its implications for our understanding of the universe. The multiverse theory proposes that our universe is just one of many, each with its own physical laws and properties. According to some models, inflation could create countless universes, each emerging from its own quantum fluctuation. This idea expands our understanding of reality and suggests that the Big Bang was not a unique event. While the multiverse theory is intriguing, it remains speculative due to the lack of direct evidence. Next, we'll explore other theories about what might have existed before the Big Bang. The cyclic universe theory suggests that the universe undergoes endless cycles of expansion and contraction. Instead of a single Big Bang, there could be a series of bangs and crunches, with each cycle giving rise to a new universe. This model addresses some of the problems with the traditional Big Bang theory, such as the question of what happened before the beginning. However, it also raises new questions about the mechanisms driving these cycles. Let's look at the evidence and challenges for the cyclic universe theory. Bounce cosmology is a variation of the cyclic universe theory. It proposes that the universe contracts to a high-density state and then bounces back into expansion, avoiding a singularity. This model suggests that the universe could have existed before the Big Bang, with each bounce marking a new beginning. Bounce cosmology is supported by some mathematical models, but lacks direct observational evidence. Next, we'll examine the philosophical implications of these theories. The question of what happened before the Big Bang is not just scientific, it's deeply philosophical. It challenges our understanding of time, causality, and existence. Some philosophers argue that time itself began with the Big Bang, making the concept of before meaningless. Others suggest that the universe could be eternal, with no true beginning or end. These ideas highlight the limits of human knowledge and the importance of exploring both scientific and philosophical perspectives. Next, we'll discuss the role of mathematics in cosmology. Mathematics is the language of the universe, allowing scientists to model and predict cosmic phenomena. Equations like Einstein's general relativity and quantum mechanics provide frameworks for understanding the universe's origin. However, mathematical models often reach their limits when describing singularities, or the moments before the Big Bang. This has led researchers to develop new theories, such as string theory and loop quantum gravity, which may offer deeper insights. Next, we'll explore string theory and its implications for the universe's beginning. String theory is a theoretical framework that attempts to unify all fundamental forces by describing particles as tiny, vibrating strings. In string theory, the universe may have extra dimensions beyond the familiar 3 of space and 1 of time. Some models suggest that our universe could be a brane floating in a higher dimensional space, and collisions between branes might trigger events like the Big Bang. While string theory is mathematically elegant, it remains unproven due to the lack of experimental evidence. Next, we'll look at loop quantum gravity. Loop quantum gravity is another attempt to unify quantum mechanics and general relativity. It proposes that space and time are made up of tiny loops, forming a discrete structure rather than a continuous one. This theory suggests that the universe could avoid a singularity, with the Big Bang representing a transition from a previous state. Loop quantum gravity offers a possible explanation for what happened before the Big Bang, but it is still under development. Next, we'll discuss the concept of time and its role in the universe's origin. Time is a fundamental concept in physics, but its origin remains mysterious. Some theories suggest that time began with the Big Bang, while others propose that it existed before. The nature of time affects our understanding of causality and the universe's evolution. If time started with the Big Bang, then asking what happened before may not make sense. Alternatively, if time is eternal, the universe could have existed in some form forever. Let's explore how scientists study the nature of time. Scientists study time using both theoretical and experimental methods. Atomic clocks, astronomical observations, and mathematical models help researchers understand how time behaves in different contexts. Relativity shows that time can slow down or speed up depending on gravity and motion. These studies reveal that time is not absolute but relative, shaped by the universe's structure. Understanding time is crucial for unraveling the mysteries of the universe's origin. Next, we'll look at the role of entropy and the arrow of time. Entropy is a measure of disorder in a system and plays a key role in the direction of time. The arrow of time refers to the fact that time moves forward, from past to future, driven by increasing entropy. In the early universe, entropy was low, allowing for the formation of complex structures. As the universe evolves, entropy increases, leading to the eventual heat death. Understanding entropy helps scientists explain why time appears to flow in one direction. Next, we'll discuss the concept of the heat death of the universe. The heat death is a theoretical scenario in which the universe reaches maximum entropy and can no longer sustain processes that increase order. In this state, all energy is evenly distributed, and no life or structure can exist. The heat death is predicted to occur trillions of years in the future, but it raises questions about the universe's ultimate fate. If the universe is cyclic, heat death could be followed by a new beginning. Next, we'll explore the concept of nothingness and how it relates to the universe's origin. The idea of nothingness is central to discussions about the universe's origin. Philosophers and scientists debate whether true nothingness can exist or if it is always filled with quantum fluctuations. Some theories suggest that the universe emerged from a quantum vacuum, which is not truly empty but teeming with energy. This challenges our intuition and forces us to rethink what nothing means. Next, we'll look at the role of quantum vacuum in the birth of the universe. A quantum vacuum is a state with the lowest possible energy, but it is not empty. It contains fluctuating fields and particles that pop in and out of existence. Some cosmological models propose that the universe was born from a quantum vacuum, with a fluctuation triggering the Big Bang. This idea connects quantum mechanics with cosmology and offers a possible explanation for how the universe could arise from nothing. Next, we'll discuss the limitations of our current theories. Despite advances in cosmology, our current theories have limitations. The lack of a unified theory of quantum gravity prevents us from fully understanding the universe's origin. Observational evidence is scarce, and many models remain speculative. Scientists continue to develop new frameworks and seek clues in cosmic phenomena. The quest to understand what happened before the Big Bang is ongoing, with each discovery bringing us closer to the truth. Next, we'll look at the role of observation and experimentation in cosmology. Observation and experimentation are essential for advancing our understanding of the universe. Telescopes, satellites, and particle accelerators provide data about cosmic phenomena. Experiments like the Large Hadron Collider help scientists study fundamental particles and forces. These tools allow researchers to test theories and refine models, bringing us closer to understanding the universe's origin. Next, we'll discuss the importance of collaboration in scientific discovery. Scientific discovery is a collaborative effort, involving researchers from around the world. International projects like the Hubble Space Telescope and CERN bring together experts in physics, astronomy, and engineering. Collaboration accelerates progress and enables the sharing of ideas and resources. By working together, scientists can tackle complex questions about the universe's origin. Next, we'll look at the role of technology in expanding our knowledge. Advances in technology have revolutionized our understanding of the universe. Powerful telescopes, supercomputers, and sophisticated detectors allow scientists to observe distant galaxies and simulate cosmic events. Technology enables the collection and analysis of vast amounts of data, revealing patterns and insights that were previously inaccessible. As technology continues to evolve, our ability to explore the universe's origins will grow. Next, we'll discuss the role of imagination and creativity in science. Imagination and creativity are vital for scientific progress. Many breakthroughs begin with bold ideas and innovative thinking. Theories about the universe's origin, such as the multiverse and string theory, require scientists to think beyond conventional boundaries. Imagination drives the development of new models and inspires the search for evidence. By embracing creativity, researchers can explore possibilities that may one day become scientific reality. Next, we'll look at the importance of education in cosmology. Education plays a crucial role in advancing cosmology. Universities, research institutes, and online platforms provide opportunities for learning and discovery. By studying physics, astronomy, and mathematics, students can contribute to our understanding of the universe. Education fosters curiosity and encourages critical thinking, preparing the next generation of scientists. Next, we'll discuss the impact of public outreach and science communication. Public outreach and science communication are essential for sharing discoveries and inspiring interest in cosmology. Museums, documentaries, and online content make complex ideas accessible to everyone. Outreach helps bridge the gap between scientists and the public, fostering appreciation for the universe's mysteries. By engaging with the community, researchers can encourage support for scientific research and education. Next, we'll look at the role of art and culture in shaping our understanding of the cosmos. Art and culture have always played a role in shaping our understanding of the cosmos. From ancient myths to modern paintings, humans express their fascination with the universe through creativity. Artistic representations inspire scientific inquiry and help communicate complex ideas. Culture influences how we interpret discoveries and imagine the universe's origin. Next, we'll discuss the importance of curiosity and wonder in scientific exploration. Curiosity and wonder drive scientific exploration. The desire to understand the universe's origin motivates researchers to ask big questions and seek answers. Wonder inspires creativity and fuels the pursuit of knowledge. By embracing curiosity, scientists can push the boundaries of what is known and explore the unknown. Next, we'll look at the role of uncertainty and the acceptance of mystery in science. Uncertainty is an inherent part of scientific inquiry. Many questions about the universe's origin remain unanswered, and new discoveries often raise more questions. Scientists accept uncertainty as a driving force for exploration, using it to refine theories and seek evidence. Embracing mystery allows researchers to remain open-minded and adapt to new information. Next, we'll discuss the importance of skepticism and critical thinking. Skepticism and critical thinking are essential for scientific progress. Researchers question assumptions, test hypotheses, and evaluate evidence. Critical thinking helps scientists avoid bias and ensures that theories are based on reliable data. By applying skepticism, researchers can challenge existing models and develop new ideas. Next, we'll look at the role of peer review and scientific consensus. Peer review and scientific consensus are important for validating discoveries and theories. Researchers submit their work to journals where experts evaluate the methods and conclusions. Peer review ensures that scientific findings are reliable and reproducible. Consensus emerges when multiple studies support a theory, strengthening its credibility. This process helps build a foundation for further exploration. Next, we'll discuss the impact of new discoveries on our understanding of the universe. New discoveries constantly reshape our understanding of the universe. Observations of cosmic phenomena, advances in technology, and theoretical breakthroughs reveal new insights. Each discovery challenges existing models and inspires further research. The quest to understand what happened before the Big Bang is ongoing, with every finding bringing us closer to the truth. Next, we'll look at the future of cosmology and the questions that remain. The future of cosmology is bright, with new technologies and theories on the horizon. Upcoming telescopes, experiments, and collaborations promise to reveal more about the universe's origin. Scientists hope to develop a unified theory of quantum gravity and uncover evidence for models like the multiverse or bounce cosmology. The journey is ongoing, and the mysteries of the cosmos continue to inspire exploration. Next, we'll summarize the key points from our journey. Throughout this video, we've explored the mysteries of the universe's origin. We've discussed the Big Bang Theory, cosmic inflation, quantum mechanics, and the multiverse. We've examined philosophical questions, mathematical models, and the role of technology and collaboration. The quest to understand what happened before the Big Bang is ongoing, with each discovery bringing us closer to the truth. Let's reflect on the significance of these questions for humanity. The search for the universe's origin is more than a scientific endeavor, it's a quest for meaning. Understanding where we come from shapes our worldview and inspires curiosity. These questions connect us to the cosmos and highlight the importance of exploration. By seeking answers, humanity continues to grow and evolve. Next, we'll discuss the role of humility in scientific inquiry. Humility is essential for scientific progress. Researchers acknowledge the limits of their knowledge and remain open to new ideas. The mysteries of the universe remind us that there is much we do not know. By embracing humility, scientists can continue to explore and discover. Next, we'll look at the importance of perseverance in the quest for understanding. Perseverance is key to scientific discovery. The search for answers about the universe's origin requires patience and determination. Researchers face challenges and setbacks, but continue to push forward. Perseverance enables scientists to overcome obstacles and achieve breakthroughs. Next, we'll discuss the role of hope and optimism in exploration. Hope and optimism drive scientific exploration. The belief that answers exist motivates researchers to continue their quest. Optimism inspires creativity and encourages the pursuit of knowledge. By maintaining hope, scientists can face uncertainty and embrace the unknown. Next, we'll reflect on the interconnectedness of science and philosophy. Science and philosophy are deeply interconnected. Scientific discoveries raise philosophical questions about existence, time, and causality. Philosophy provides frameworks for interpreting scientific findings and exploring the meaning of the universe. By combining science and philosophy, humanity can gain a deeper understanding of the cosmos. Next, we'll discuss the importance of asking big questions. Asking big questions is essential for progress. The mysteries of the universe inspire curiosity and drive exploration. By seeking answers to questions like, what happened before the Big Bang? Humanity pushes the boundaries of knowledge. Big questions encourage innovation and foster a sense of wonder. Next, we'll summarize the journey and look forward to future discoveries. The journey to understand the universe's origin is ongoing. New discoveries, technologies, and theories will continue to shape our understanding. By embracing curiosity, imagination, and collaboration, humanity can explore the mysteries of the cosmos. The quest for knowledge is never-ending, and the universe remains a source of inspiration. Let's continue to ask questions and seek answers together. Thank you for joining us on this exploration of the universe's origin. We've journeyed through scientific theories, philosophical questions, and the wonders of the cosmos. The mysteries of the universe continue to inspire curiosity and discovery. Stay tuned for more adventures as we seek to unravel the secrets of existence. Until next time, keep exploring and wondering about the universe. Welcome to our deep dive into the fascinating world of black holes. These cosmic phenomena have captured the imagination of scientists and the public alike. Today, we'll explore how black holes form and what happens inside them. From their mysterious origins to the mind-bending physics at their core, black holes challenge our understanding of the universe. Let's begin by unraveling the basics of what a black hole is and why it's such an important topic in astrophysics. Get ready for a journey through space, time, and gravity as we uncover the secrets of these enigmatic objects. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape its pull. This extreme gravitational force is created when a massive object collapses under its own weight. The boundary surrounding a black hole is called the event horizon. Once something crosses this boundary, it cannot return. Black holes are invisible because they do not emit light, but their presence can be detected by observing their effects on nearby stars and gas. Understanding what defines a black hole is crucial before we explore how they form. Stars are born from clouds of gas and dust, known as nebulae. Over millions of years, gravity pulls this material together, forming a protostar. As the star matures, it undergoes nuclear fusion, converting hydrogen into helium and releasing energy. The life cycle of a star depends on its mass. Massive stars burn hotter and faster, while smaller stars like our Sun have longer lifespans. The fate of a star is determined by its mass, which is a key factor in black hole formation. Let's look at how the death of massive stars leads to black holes. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses, triggering a supernova, a powerful explosion that ejects the star's outer layers into space. This dramatic event leaves behind a dense core. Depending on the mass of this core, it can become a neutron star, or, if it's heavy enough, collapse further to form a black hole. Supernovae are not only spectacular, but also essential for creating black holes and dispersing elements throughout the universe. After a supernova, the remaining core's fate depends on its mass. If the core is more than about 3 times the mass of our Sun, gravity overwhelms all other forces, causing the core to collapse into a black hole. This process is known as core collapse. The resulting black hole is incredibly dense, with all its mass concentrated in a tiny region. This marks the birth of a stellar mass black hole, one of the most common types found in the universe. Black holes come in several types, distinguished by their mass and origin. Stellar mass black holes form from collapsing stars. Supermassive black holes, found at the centers of galaxies, have millions or billions of times the mass of our Sunday. Intermediate mass black holes are less common, and primordial black holes may have formed in the early universe. Each type has unique characteristics and plays a different role in cosmic evolution. Supermassive black holes are found at the centers of most galaxies, including our own Milky Way. Their formation is still a mystery, but they may grow by merging with other black holes or by accreting vast amounts of gas and stars. These giants influence galaxy formation and evolution, affecting the motion of stars and the distribution of matter. Understanding supermassive black holes helps us grasp the structure of the universe. Primordial black holes are hypothetical objects that may have formed in the early universe shortly after the Big Bang. Unlike stellar or supermassive black holes, these could be much smaller and formed from density fluctuations in the young cosmos. If they exist, primordial black holes could help explain dark matter and other cosmic mysteries. Their existence remains unproven, but they are a fascinating possibility in astrophysics. The event horizon is the boundary around a black hole where escape becomes impossible. It marks the point at which the gravitational pull is so strong that not even light can escape. Anything crossing the event horizon is lost to the outside universe. The event horizon is crucial in defining a black hole and is the source of many mysteries, including the information paradox. Let's explore what happens as objects approach this boundary. As an object approaches a black hole, it experiences extreme tidal forces. These forces stretch the object vertically and compress it horizontally, a process known as spaghettification. The closer the object gets to the event horizon, the more intense the stretching becomes. For stellar mass black holes, this effect is so strong that it would tear apart any object long before it reaches the center. Spaghettification is a dramatic illustration of the power of black hole gravity. Once an object crosses the event horizon, it is cut off from the outside universe. The laws of physics as we know them begin to break down. Time and space become distorted, and the object inevitably moves toward the black hole's center, or singularity. No information can escape from inside the event horizon, making it impossible to observe what happens directly. This region is shrouded in mystery and is a focus of intense scientific research. At the heart of a black hole lies the singularity, a point where gravity is infinitely strong and space-time curves infinitely. All the mass of the black hole is concentrated here. The singularity is a place where our current understanding of physics fails. General relativity predicts its existence, but quantum mechanics cannot describe it. The singularity remains one of the greatest mysteries in science, challenging our theories and inspiring new research. Black holes dramatically distort space and time. Near the event horizon, time slows down relative to an outside observer, a phenomenon known as time dilation. Space is warped, and the paths of objects and light are bent by gravity. This distortion is predicted by Einstein's theory of general relativity and has been confirmed by observations. The extreme environment near a black hole provides a unique laboratory for studying the nature of space-time. Black holes are not entirely black. Stephen Hawking predicted that they emit a faint radiation, now known as Hawking radiation. This process occurs because quantum effects near the event horizon allow particles to escape. Over time, Hawking radiation causes black holes to lose mass and eventually evaporate. This discovery links quantum mechanics and general relativity, offering new insights into the fate of black holes. Through Hawking radiation, black holes can slowly lose mass and energy. This process is extremely slow for large black holes, but smaller ones could evaporate more quickly. Eventually, a black hole may disappear entirely, leaving behind only its radiation. Black hole evaporation is a theoretical concept, but it has profound implications for the ultimate fate of these objects and the conservation of information. The information paradox arises because black holes seem to destroy information about the objects that fall into them. According to quantum mechanics, information cannot be lost, but black holes appear to erase it. This paradox has sparked intense debate and research, leading to new theories about how information might be preserved or encoded in Hawking radiation. Solving the information paradox is a major challenge in modern physics. Black holes cannot be seen directly because they emit no light. However, astronomers observe their effects on nearby stars, gas, and dust. When material falls into a black hole, it forms an accretion disk and emits X-rays. The motion of stars around invisible objects also reveals the presence of black holes. Recent breakthroughs, like the first image of a black hole's shadow, have provided new ways to study these mysterious objects. Material spiraling into a black hole forms an accretion disk, a hot, glowing ring of gas and dust. Friction and gravity heat the disk, causing it to emit X-rays and other radiation. The dynamics of accretion disks are complex and reveal much about the behavior of black holes. Studying these disks helps astronomers understand how black holes grow and interact with their surroundings. Some black holes produce powerful jets of particles that shoot out from their poles at nearly the speed of light. These jets are created by magnetic fields and the intense energy in the accretion disk. Jets can extend for thousands of light years and influence their environment, including galaxy formation. Observing jets helps scientists learn about the extreme conditions near black holes. When black holes merge, they create ripples in spacetime called gravitational waves. These waves travel across the universe and can be detected by sensitive instruments on Earth. The discovery of gravitational waves has opened a new window for studying black holes and other cosmic events. It confirms predictions of Einstein's theory and provides direct evidence of black hole mergers. Black holes can merge with each other, forming larger black holes. These mergers release enormous amounts of energy in the form of gravitational waves. Observing black hole mergers helps scientists understand the population and evolution of black holes in the universe. The detection of these events is a major achievement in modern astronomy. Black holes, especially supermassive ones, play a crucial role in shaping galaxies. Their gravity influences the motion of stars and gas, and their jets can regulate star formation. The relationship between black holes and their host galaxies is a key area of research. Understanding this connection helps us learn how galaxies grow and evolve over billions of years. Some theories suggest that black holes could be linked to dark matter, the mysterious substance that makes up most of the universe's mass. Primordial black holes, if they exist, might account for some or all of dark matter. Studying black holes could provide clues about the nature and distribution of dark matter, one of the biggest mysteries in cosmology. Black holes are described mathematically by solutions to Einstein's equations of general relativity. The most famous solution is the Schwarzschild metric, which describes a non-rotating, uncharged black hole. Other solutions include the Kerr metric for rotating black holes and the Reissner-Nordström metric for charged ones. These mathematical models help scientists predict black hole behavior and properties. Many black holes rotate, and this rotation affects their properties. The Kerr metric describes rotating black holes. which have an ergosphere, a region outside the event horizon where objects cannot remain stationary. Rotation can also affect the emission of jets and the dynamics of accretion disks. Understanding rotating black holes is important for studying real-world black holes in space. Some theoretical black holes carry electric charge. The Reissner-Nordström metric describes these objects. Charged black holes have different event horizons and can interact with electromagnetic fields. While no charged black holes have been observed, studying them helps scientists explore the limits of general relativity and quantum theory. Black holes obey laws similar to thermodynamics. They have entropy, temperature, and can exchange energy. The area of the event horizon is related to entropy, and Hawking radiation gives black holes a temperature. Black hole thermodynamics connects gravity, quantum mechanics, and statistical physics, offering new ways to understand the universe. The singularity at the center of a black hole is where quantum gravity becomes important. Current theories cannot fully describe this region. Scientists are working to develop a theory of quantum gravity that unifies general relativity and quantum mechanics. Black holes provide a unique testing ground for these ideas, pushing the boundaries of physics. Some theories suggest that black holes could be connected to wormholes, hypothetical tunnels through space-time. Wormholes might allow travel between distant regions of the universe. While no evidence exists for wormholes, studying black holes helps scientists explore these possibilities and the nature of space-time. The extreme space-time curvature near black holes has led to speculation about time travel. Some solutions to Einstein's equations suggest that closed time-like curves could exist near rotating black holes. While time travel remains science fiction, black holes inspire new ideas about the nature of time and causality. Black holes can form in binary star systems where two stars orbit each other. When one star explodes as a supernova, its core may collapse into a black hole. The remaining star can transfer material to the black hole, creating an accretion disk and emitting X-rays. Binary systems are important for studying black hole formation and evolution. Star clusters are dense groups of stars, and black holes can form within them. Collisions and mergers between stars increase the chances of black hole formation. Studying black holes in star clusters helps astronomers understand their population and the dynamics of dense stellar environments. Some black holes are associated with gamma-ray bursts, powerful explosions that emit intense radiation. These bursts occur when massive stars collapse or when black holes merge. Gamma-ray bursts are among the most energetic events in the universe and provide clues about black hole formation and cosmic evolution. Black holes grow by accreting matter and merging with other black holes. The rate of growth depends on the availability of material and the environment. Supermassive black holes can grow rapidly in the centers of galaxies, while stellar mass black holes grow more slowly. Understanding black hole growth is key to studying their evolution and impact on the universe. Black holes play a role in cosmic recycling by dispersing elements through supernovae and accretion disk outflows. These processes enrich the interstellar medium, providing material for new stars and planets. Black holes are not just destructive, they contribute to the ongoing cycle of matter in the universe. Black holes have become icons in popular culture, appearing in movies, books, and art. Their mysterious nature and dramatic effects inspire stories about space exploration and the unknown. While fictional portrayals often exaggerate their properties, they help spark interest in science and encourage curiosity about the universe. Recent discoveries have revolutionized our understanding of black holes. The first image of a black hole's shadow, detection of gravitational waves, and new observations of accretion disks have provided unprecedented insights. Ongoing research continues to reveal surprises and deepen our knowledge of these cosmic objects. The study of black holes is rapidly evolving. Future research aims to answer questions about their formation, growth, and the nature of singularities. New telescopes and instruments will provide better observations, and advances in theory may solve long-standing puzzles like the information paradox. Black holes remain at the frontier of science. Black holes have a profound impact on physics, challenging our understanding of gravity, quantum mechanics, and space-time. They inspire new theories and experiments, pushing the limits of what we know. Studying black holes helps scientists develop a deeper understanding of the universe and its fundamental laws. Black holes are essential components of the universe. They influence galaxy formation, cosmic evolution, and the distribution of matter. Their extreme properties provide unique opportunities for studying fundamental physics. Black holes remind us of the vastness and complexity of the cosmos. To summarize, black holes form when massive stars collapse after exhausting their nuclear fuel. Supernova explosions leave behind dense cores, which can become black holes if their mass is sufficient. Other types, like supermassive and primordial black holes, have different origins. Understanding formation is key to unraveling their mysteries. Inside black holes, gravity dominates, and space-time is warped beyond recognition. The event horizon marks the boundary, and the singularity lies at the core. Phenomena like spaghettification, Hawking radiation, and the information paradox illustrate the strange physics inside. These mysteries drive ongoing research and inspire new theories. Black holes matter because they challenge our understanding of physics and the universe. They are laboratories for extreme gravity, quantum effects, and space-time. Studying black holes helps us answer fundamental questions about the nature of reality and our place in the cosmos. The exploration of black holes is far from over. New discoveries, theories, and observations continue to expand our knowledge. Black holes remain at the forefront of science, inspiring curiosity and wonder. As we probe deeper into their mysteries, we uncover more about the universe and ourselves. Black holes are among the most mysterious and fascinating objects in the universe. Their formation, inner workings, and impact on cosmic evolution continue to intrigue scientists and the public. By studying black holes, we push the boundaries of knowledge and deepen our understanding of the universe. The journey into black hole science is ongoing, and the mysteries they hold promise to reveal even more about the cosmos. Welcome to our journey through the cosmos, where we unravel the fascinating story of how stars are born, live, and eventually die. Stars are the fundamental building blocks of the universe, illuminating the night sky and shaping galaxies. Their life cycles are both dramatic and beautiful, involving processes that span millions to billions of years. In this video, we'll explore the stages of stellar evolution, from their humble beginnings in vast clouds of gas and dust to their spectacular ends as white dwarfs, neutron stars, or black holes. Let's begin by understanding what makes a star and why their life stories matter to us all. Stars are born in regions known as stellar nurseries, which are vast clouds of gas and dust called nebulae. These nebulae are scattered throughout galaxies and provide the raw materials for star formation. Within these clouds, gravity begins to pull particles together, forming dense clumps. As these clumps grow, their internal pressure and temperature increase, setting the stage for the birth of a new star. The process is slow and can take millions of years, but it is the first step in the life cycle of every star. Let's take a closer look at these cosmic cradles and how they nurture the beginnings of stellar life. Nebulae are not just beautiful to look at, they are the actual birthplaces of stars. These clouds can be hundreds of light years across and contain enough material to form thousands of stars. The most famous nebulae, like the Orion Nebula, are visible even with small telescopes. Within these nebulae, regions of higher density begin to collapse under their own gravity, leading to the formation of protostars. The interplay of gravity, pressure, and temperature in these environments is crucial for star formation. As we observe nebula, we witness the earliest stages of stellar evolution unfolding before our eyes. As dense regions within nebulae collapse, they form protostars. A protostar is a young star still gathering mass from its parent cloud. During this stage, the core temperature rises, but nuclear fusion has not yet begun. The protostar is often surrounded by a disk of material which may eventually form planets. This phase is marked by intense activity, including jets of gas shooting out from the poles and strong winds that clear away surrounding material. The protostar stage is a critical transition, setting the conditions for the star's future evolution. When the core of a protostar becomes hot and dense enough, nuclear fusion ignites. This is the moment when a star truly comes to life. Hydrogen atoms fuse to form helium, releasing enormous amounts of energy. This energy creates outward pressure that balances the force of gravity, stabilizing the star. The star enters the main sequence phase, where it will spend most of its life. The ignition of nuclear fusion marks the transition from a protostar to a fully fledged star, shining brightly in the cosmos. The main sequence is the longest phase in a star's life. During this period, the star steadily burns hydrogen in its core, producing light and heat. The balance between gravity and the pressure from fusion keeps the star stable. Our Sun is currently a main sequence star, shining for billions of years. The mass of the star determines how long it will stay in this phase. Massive stars burn their fuel quickly, while smaller stars can last much longer. The main sequence is where stars spend most of their existence, providing energy to their planetary systems. A star's mass is the key factor in determining its lifespan and fate. Massive stars burn their fuel rapidly, shining brightly but living short lives. Smaller stars, like red dwarfs, burn slowly and can last for tens of billions of years. The mass also influences the star's eventual death, dictating whether it will become a white dwarf, neutron star, or black hole. Understanding stellar mass helps us predict the evolution and ultimate fate of stars across the universe. Red dwarfs are the most common and longest-lived stars in the universe. These small, cool stars burn hydrogen slowly, allowing them to shine for tens of billions of years. Unlike massive stars, red dwarfs never become supernovae. Instead, they gradually fade away, ending their lives as cool, dim remnants. Their longevity makes them important for understanding the long-term evolution of galaxies and the potential for life on planets orbiting them. Massive stars live fast and die young. Their enormous mass causes them to burn through their fuel quickly, resulting in intense brightness and heat. These stars often end their lives in spectacular explosions called supernovae, which can outshine entire galaxies for a brief period. The remnants of these explosions can become neutron stars or black holes. Massive stars play a crucial role in enriching the universe with heavy elements, which are essential for planets and life. Stellar evolution is the process by which a star changes over time. It begins with the collapse of a nebula, progresses through the protostar and main sequence phases, and ends with the star's death. The path a star takes depends on its mass, with different outcomes for low-mass and high-mass stars. This overview helps us understand the diversity of stars and their impact on the universe. Each stage is marked by unique physical processes and dramatic changes. The core of a main sequence star is a powerhouse of hydrogen fusion. Here, hydrogen atoms combine to form helium, releasing energy that powers the star. This process is known as the proton-proton chain reaction in smaller stars, while larger stars use the CNO cycle. The energy produced keeps the star stable and shining. Hydrogen fusion is the fundamental process that defines the main sequence phase and sustains the star for most of its life. A star remains stable during its main sequence phase due to the balance between gravity pulling inward and pressure from fusion pushing outward. This equilibrium is called hydrostatic balance. If gravity overpowers fusion, the star collapses. If fusion dominates, the star expands. Maintaining this balance is essential for the star's longevity and stability. The interplay of forces shapes the star's structure and behavior throughout its life. Eventually, a star exhausts the hydrogen in its core. Without fresh fuel, fusion slows down, and the core begins to contract under gravity. This marks the end of the main sequence phase and the beginning of dramatic changes. The star's outer layers expand, and it enters the next stage of its evolution. The depletion of hydrogen is a turning point, leading to new fusion processes and the transformation of the star. When hydrogen is depleted, the star's core contracts and heats up, causing the outer layers to expand and cool. The star becomes a red giant, much larger and brighter than before. In this phase, helium fusion begins in the core, producing heavier elements like carbon and oxygen. The red giant phase is a period of instability, with the star shedding material into space. This stage is especially important for low and medium mass stars, including our Sun. During the red giant phase, the star's core becomes hot enough for helium fusion. Helium atoms combine to form carbon and oxygen, releasing energy. In more massive stars, fusion continues, creating even heavier elements up to iron. These processes enrich the universe with the building blocks for planets and life. Helium fusion marks a new chapter in the star's evolution, leading to further changes and eventual death. As a low or medium mass star nears the end of its life, it sheds its outer layers, creating a planetary nebula. The core remains as a hot, dense remnant, while the expelled material forms a glowing shell around it. Planetary nebulae are stunning objects, often displaying intricate shapes and colors. This process marks the transition from the red giant phase to the final stage of the star's life. After the planetary nebula phase, the remaining core becomes a white dwarf. This is a small, dense star with no ongoing fusion. White dwarfs slowly cool and fade over billions of years. They represent the final stage for low and medium mass stars. Despite their small size, white dwarfs are incredibly dense, packing the mass of the Sun into a volume similar to Earth. Massive stars end their lives in spectacular supernova explosions. When the core can no longer support itself, it collapses, triggering a violent explosion that blasts material into space. Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies. The explosion creates and disperses heavy elements, enriching the cosmos and paving the way for new stars and planets. The remnants of some supernovae become neutron stars. These are incredibly dense objects, with a mass greater than the Sun compressed into a sphere only a few kilometers across. Neutron stars are composed almost entirely of neutrons and have intense magnetic fields. Some spin rapidly, emitting beams of radiation known as pulsars. Neutron stars are fascinating endpoints for massive stars, showcasing extreme physics. The most massive stars can end their lives as black holes. When the core collapses beyond a certain point, gravity becomes so strong that nothing, not even light, can escape. Black holes are mysterious objects, with an event horizon marking the boundary beyond which information is lost. They play a key role in shaping galaxies and influencing cosmic evolution. The formation of black holes is the ultimate fate for the largest stars. After a star dies, its remnants continue to impact the universe. White dwarfs, neutron stars, and black holes are all examples of stellar remnants. These objects can interact with their surroundings, influencing the formation of new stars and planets. Stellar remnants are important for understanding the ongoing evolution of galaxies and the recycling of cosmic material. Stars are often born in groups called star clusters. These clusters can be open, with loosely bound stars, or globular, with tightly packed stars. Star clusters provide valuable insights into stellar evolution, as their members share similar ages and compositions. Observing clusters helps astronomers understand how stars interact and evolve together. Many stars are part of binary or multiple star systems, where two or more stars orbit each other. These systems can influence stellar evolution, especially when stars exchange material. Binary interactions can lead to phenomena like novae, X-ray binaries, and even the merging of stars. Understanding these systems adds complexity to the story of stellar life and death. Throughout their lives, stars lose mass through stellar winds. These winds are streams of particles ejected from the star's surface, carrying material into space. Mass loss affects the star's evolution, especially in massive stars, where strong winds can strip away outer layers. Stellar winds contribute to the enrichment of the interstellar medium and the formation of new stars. Novae and supernovae are explosive events in stellar evolution. Novae occur in binary systems when material from one star accumulates on a white dwarf, triggering a sudden burst of fusion. Supernovae, as discussed earlier, are the dramatic deaths of massive stars. Both events release energy and material, influencing the surrounding space and contributing to cosmic recycling. Stars are responsible for creating most of the heavy elements in the universe. Fusion in stellar cores produces elements up to iron, while supernovae create even heavier elements like gold and uranium. These elements are dispersed into space, becoming part of new stars, planets, and life. The process of nucleosynthesis is central to cosmic evolution and the diversity of matter. The material produced and dispersed by stars is essential for planet formation. Elements like carbon, oxygen, and iron become part of planetary systems, providing the building blocks for planets and life. The cycle of star birth and death ensures a continuous supply of material for new worlds. Understanding stellar evolution helps us appreciate the origins of planets and the potential for life elsewhere. Stars drive the evolution of galaxies. Their formation, life, and death shape the structure and composition of galaxies. Supernovae and stellar winds influence the interstellar medium, triggering new star formation and redistributing material. The ongoing cycle of stellar evolution is a key factor in the dynamic history of galaxies across the universe. Astronomers use telescopes and other instruments to observe stars at every stage of their life cycles. By studying nebula, main sequence stars, red giants, supernovae, and remnants, scientists piece together the story of stellar evolution. Observations across different wavelengths reveal details about star formation, fusion processes, and stellar deaths. These studies deepen our understanding of the universe and our place within it. Gravity is the driving force behind star formation and evolution. It causes nebulae to collapse, triggers fusion in protostars, and shapes the fate of dying stars. Gravity determines whether a star becomes a white dwarf, neutron star, or black hole. Its influence is felt throughout the cosmos, guiding the life cycles of stars and the structure of galaxies. Star formation occurs throughout the universe, in galaxies near and far. Different environments produce different types of stars, from massive giants to tiny red dwarfs. The diversity of star formation reflects the variety of conditions in the cosmos. By studying star formation in different galaxies, astronomers learn about the history and evolution of the universe. The life cycles of stars can vary depending on the galaxy they inhabit. Some galaxies are rich in gas and dust, supporting active star formation. Others are older and quieter, with fewer new stars. The environment influences the types of stars formed and their evolution. Comparing stellar evolution across galaxies helps us understand cosmic diversity and the factors shaping the universe. The death of stars is not the end, but a new beginning for the universe. Material expelled by dying stars is recycled into new stars, planets, and life. This cosmic recycling ensures the ongoing evolution of galaxies and the diversity of matter. The cycle of birth, life, and death is fundamental to the universe's history and future. The evolution of stars is closely linked to the search for life in the universe. Stars provide energy and elements needed for life, and their stability influences planetary environments. Understanding stellar life cycles helps us identify habitable zones and the potential for life on other worlds. The story of stars is also the story of life's possibilities across the cosmos. Stellar evolution will continue for billions of years, shaping the universe's future. As stars form, live, and die, they drive cosmic change and create new opportunities for planets and life. The ongoing cycle ensures that the universe remains dynamic and full of possibilities. Studying stellar evolution helps us anticipate the future of galaxies and the fate of the cosmos. The study of stellar evolution has transformed our understanding of the universe. By unraveling the life cycles of stars, scientists have discovered the origins of elements, the dynamics of galaxies, and the potential for life. Stellar evolution connects us to the cosmos, revealing our place in a vast and ever-changing universe. This knowledge inspires curiosity and wonder, driving further exploration. The timeline of stellar evolution spans millions to billions of years. From the collapse of a nebula to the formation of a protostar, main sequence, red giant, and eventual death, each stage is marked by unique processes. The timeline varies depending on the star's mass, with massive stars evolving quickly and small stars lasting much longer. Understanding this timeline helps us appreciate the scale and complexity of cosmic evolution. Stellar evolution is a fundamental process shaping the universe. The birth, life, and death of stars drive cosmic change, influence galaxies, and create the elements needed for planets and life. By studying stellar evolution, we gain insight into the history, structure, and future of the cosmos. The story of stars is central to understanding the universe and our place within it. The life cycles of stars have inspired countless works of art, literature, and popular culture. From science fiction stories to breathtaking images from telescopes, stellar evolution captures our imagination. The drama of star birth and death reminds us of the beauty and mystery of the universe. Popular culture helps bring the science of stars to a wider audience, fostering curiosity and appreciation. Advances in technology have revolutionized our study of stellar evolution. Telescopes, satellites, and computer models allow scientists to observe and simulate star formation, fusion, and death. Technology enables discoveries about distant stars and galaxies, expanding our knowledge of the universe. The interplay between science and technology drives progress in understanding stellar life cycles. The future of stellar evolution research is bright. New missions and telescopes will reveal more about star formation, fusion, and death. Scientists hope to discover new types of stars, understand extreme physics, and explore the origins of elements. Future exploration will deepen our connection to the cosmos and inspire new generations of astronomers. Studying stellar evolution gives us a cosmic perspective. We see the interconnectedness of stars, galaxies, and life. The processes that shape stars also shape the universe and our own existence. This perspective encourages us to explore, learn, and appreciate the wonders of the cosmos. Stellar evolution is a story of change, connection, and discovery. In summary, stars are born in nebulae, live through fusion-powered phases, and die in various ways depending on their mass. Their life cycles drive cosmic evolution, create elements, and influence galaxies. The study of stellar evolution reveals the beauty, complexity, and interconnectedness of the universe. Understanding stars helps us appreciate our place in the cosmos and the ongoing story of creation and change. Reflecting on stellar evolution, we see the profound impact stars have on the universe. Their birth, life, and death shape galaxies, create elements, and support life. The story of stars is a story of transformation, connection, and renewal. By studying stellar evolution, we gain insight into the past, present, and future of the cosmos. This knowledge inspires wonder and drives our quest to explore the universe. The life cycles of stars are an ongoing story, shaping the universe for billions of years. From their birth in nebulae to their dramatic deaths and the recycling of material, stars drive cosmic evolution. Their influence is felt in galaxies, planets, and life itself. As we continue to study and explore, the story of stars will reveal new mysteries and deepen our understanding of the cosmos. Thank you for joining this journey through the life, evolution, and death of stars across the universe. Welcome to our journey, exploring the vastness of the universe. Have you ever wondered why the universe is so incredibly huge, and how scientists manage to measure its size? Today, we'll dive deep into the mysteries of space, uncovering the factors that contribute to its immense scale and the ingenious methods researchers use to quantify it. From the earliest observations to modern technology, our understanding of the universe has evolved dramatically. Let's begin by setting the stage for this cosmic adventure, examining what we mean by the universe and why its size fascinates scientists and laypeople alike. The universe is everything we know: all matter, energy, planets, stars, galaxies, and even the empty space between them. Scientists define the universe as the totality of existence, stretching beyond what we can see or measure. This definition is crucial because it sets the boundaries for what we attempt to study and measure. When we talk about the universe's size, we're referring to the observable universe, the part we can detect with our instruments. But the universe itself may be much larger, possibly infinite. Understanding this distinction helps us appreciate the challenge scientists face when measuring its vastness. The observable universe is the region of space we can see from Earth, limited by the speed of light and the age of the universe. Light from distant objects takes time to reach us, so we can only observe objects whose light has had enough time to travel to Earth since the universe began. This means the observable universe is a sphere centered on us, with a radius of about 46 billion light-years. Beyond this, there may be more universe, but it's currently inaccessible to us. Scientists focus on this observable region when measuring the universe's size. The universe's immense size is a result of its age and the speed at which it has been expanding since the Big Bang. Over 13.8 billion years, space itself has stretched, carrying galaxies farther apart. This expansion means that the universe is not static, it's constantly growing, making its scale almost incomprehensible. The vast distances between stars and galaxies are a direct consequence of this ongoing expansion. Scientists believe that the universe may be infinite, but the observable part is limited by how far light has traveled since the beginning. The Big Bang theory is the leading explanation for the origin of the universe. It suggests that the universe began as a hot, dense point and has been expanding ever since. This expansion is responsible for the universe's vast size. The Big Bang also set the stage for the formation of galaxies, stars, and planets. By studying the cosmic microwave background radiation, scientists have confirmed the universe's age and its ongoing expansion. Understanding the Big Bang is key to grasping why the universe is so huge and how its size has changed over time. Cosmic expansion refers to the stretching of space itself, causing galaxies to move away from each other. This phenomenon was first observed by Edwin Hubble, who noticed that distant galaxies are receding from us, with their light shifted toward the red end of the spectrum, a process called redshift. The rate of expansion is measured by the Hubble constant. This expansion explains why the universe is so large and why its size continues to increase. Scientists use these observations to estimate the universe's age and size. Edwin Hubble's groundbreaking discovery in the 1920s changed our understanding of the universe. By observing distant galaxies, he found that their light was redshifted, indicating they were moving away from us. This led to the realization that the universe is expanding. Hubble's work provided the first evidence that the universe is not static, but dynamic and growing. His observations laid the foundation for modern cosmology and our current methods of measuring the universe's size. Redshift is a key concept in measuring the universe. When galaxies move away from us, their light stretches, shifting toward the red end of the spectrum. The greater the redshift, the farther the galaxy is from us. Scientists use redshift to determine distances and the rate of expansion. By analyzing the light from distant galaxies, researchers can map the universe's structure and estimate its size. Redshift is a fundamental tool in cosmology, helping us understand the universe's vastness. Measuring distances in space is a complex task. Scientists use several methods, including parallax, standard candles, and redshift. Parallax involves observing the apparent shift of nearby stars as Earth orbits the Sunday. Standard candles, like Cepheid variables and supernovae, have known brightness, allowing researchers to calculate their distance. Redshift is used for more distant galaxies. These techniques help scientists build a cosmic distance ladder, enabling them to measure the universe's size step by step. The cosmic distance ladder is a series of methods used to measure distances in the universe. Each rung of the ladder relies on different techniques, starting with parallax for nearby stars, then moving to standard candles for more distant objects, and finally, redshift for the farthest galaxies. This approach allows scientists to extend their measurements from our solar system to the edge of the observable universe. The cosmic distance ladder is essential for understanding the universe's scale. The parallax method is used to measure the distance to nearby stars. As Earth moves around the Sun, the position of a star appears to shift against the background of more distant stars. By measuring this tiny angle, scientists can calculate the star's distance using simple geometry. Parallax is effective for stars within a few hundred light-years, providing the first rung of the cosmic distance ladder. This method is fundamental for establishing accurate distances in our galaxy. Standard candles are astronomical objects with known luminosity. Cepheid, variable stars, and Type Ia supernovae are the most commonly used standard candles. By comparing their observed brightness to their intrinsic brightness, scientists can determine their distance. This method is crucial for measuring distances beyond the reach of parallax. Standard candles help extend the cosmic distance ladder, allowing researchers to map the universe more accurately. Cepheid variable stars are pulsating stars whose brightness changes in a predictable pattern. The period of their pulsation is directly related to their intrinsic luminosity. By measuring the period and observed brightness, scientists can calculate the star's distance. Cepheids are vital standard candles, helping astronomers measure distances to nearby galaxies and refine the scale of the universe. Type Ia supernovae are powerful explosions of white dwarf stars. Their peak brightness is consistent, making them excellent standard candles. By observing the light curve and comparing it to known values, scientists can determine the distance to faraway galaxies. Type Ia supernovae have been instrumental in discovering the accelerating expansion of the universe and refining measurements of its size. Redshift is used to measure the distance to the most distant galaxies. As galaxies move away, their light stretches, increasing the redshift. By analyzing the redshift, scientists can estimate how far the galaxy is and how fast it's moving. This method is essential for mapping the universe's structure and understanding its expansion. Redshift measurements have revealed the universe's vast scale and helped refine its age. The Hubble constant is a key parameter in cosmology, representing the rate at which the universe expands. By measuring the redshift and distance of galaxies, scientists calculate the Hubble constant. This value helps estimate the universe's age and size. Recent measurements have refined the Hubble constant, but some discrepancies remain, leading to ongoing research and debate. The Hubble constant is central to understanding the universe's vastness. The cosmic microwave background, CMB, is the afterglow of the Big Bang, a faint radiation filling the universe. By studying the CMB, scientists gain insights into the universe's age, composition, and size. The CMB provides a snapshot of the early universe, helping researchers refine measurements of its expansion and structure. Observations of the CMB have confirmed the universe's vastness and its ongoing growth. Mapping the universe involves charting the positions and distances of galaxies, stars, and other cosmic objects. Scientists use telescopes and satellites to collect data, creating detailed maps of the cosmos. These maps reveal the large-scale structure of the universe, including clusters, filaments, and voids. Mapping helps researchers understand how the universe has evolved and provides context for its immense size. Galaxies are not evenly distributed. They form clusters and superclusters connected by vast filaments of matter. These structures span millions of light years, highlighting the universe's immense scale. Studying clusters and superclusters helps scientists understand the distribution of matter and the forces shaping the cosmos. These structures are mapped using observations of galaxies and their distances. Cosmic voids are vast, empty regions between clusters of galaxies. These voids can span hundreds of millions of light years, emphasizing the universe's enormous size. Studying voids helps scientists understand the distribution of matter and the dynamics of cosmic expansion. Voids are mapped using galaxy surveys, revealing the universe's complex structure. Dark matter and dark energy are mysterious components of the universe. Dark matter provides the gravitational glue holding galaxies together, while dark energy drives the universe's accelerated expansion. These invisible substances make up most of the universe's mass and energy, influencing its size and structure. Scientists study their effects through observations of galaxies and cosmic expansion. Observations of distant supernovae have revealed that the universe's expansion is accelerating, driven by dark energy. This discovery has profound implications for the universe's size and fate. An accelerating universe means that distant galaxies are moving away faster, increasing the observable universe's scale. Scientists continue to study this phenomenon to understand its impact on cosmic measurements. Modern telescopes and satellites are essential tools for measuring the universe. Instruments like the Hubble Space Telescope and the James Webb Space Telescope collect data from distant galaxies, stars, and cosmic phenomena. These tools allow scientists to observe farther and more accurately, refining measurements of the universe's size and structure. Technology continues to advance, expanding our view of the cosmos. The James Webb Space Telescope, JWST, is the most advanced space observatory yet. It can peer deeper into the universe, observing the earliest galaxies and stars. JWST's powerful instruments help scientists refine measurements of cosmic distances and study the universe's evolution. Its discoveries are reshaping our understanding of the universe's vastness. Radio astronomy uses radio waves to study the universe. Radio telescopes can detect signals from distant galaxies, pulsars, and cosmic phenomena invisible to optical telescopes. This method expands our ability to measure the universe's size and structure, revealing hidden aspects of the cosmos. Infrared and X-ray astronomy allow scientists to observe cosmic phenomena that are invisible in visible light. These methods reveal the structure of galaxies, star formation, and energetic events. By combining data from different wavelengths, researchers gain a more complete picture of the universe's size and complexity. Gravitational waves are ripples in spacetime caused by massive cosmic events like merging black holes. Detecting these waves provides new ways to measure the universe and study its structure. Instruments like LIGO and Virgo have opened a new window into the cosmos, expanding our understanding of its vastness. Cosmic surveys collect data from millions of galaxies, mapping the universe's structure and scale. Projects like the Sloan Digital Sky Survey and the Dark Energy Survey provide detailed maps of the cosmos, helping scientists measure its size and understand its evolution. These surveys are essential for refining our knowledge of the universe. The scale of the universe is mind-boggling. The observable universe spans about 93 billion light-years in diameter, containing billions of galaxies, each with billions of stars. The distances between objects are so vast that light takes millions or billions of years to travel from one point to another. This immense scale challenges our imagination and highlights the universe's grandeur. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. Scientists use light-years to express vast cosmic distances. For example, the nearest star to Earth, Proxima Centauri, is about 4.24 light-years away. Using light-years helps make sense of the universe's immense scale and allows researchers to communicate measurements more effectively. Galaxies are the fundamental building blocks of the universe. Each galaxy contains billions of stars, planets, and other cosmic objects. The Milky Way, our home galaxy, is just one of billions in the observable universe. Studying galaxies helps scientists understand the universe's structure and measure its size. The Milky Way is our home galaxy, a vast spiral containing hundreds of billions of stars. Its diameter is about 100,000 light-years. By studying the Milky Way's structure and comparing it to other galaxies, scientists gain insights into the universe's scale and evolution. Beyond the Milky Way, billions of other galaxies populate the universe. Each galaxy has its own unique structure, size, and history. Observing these galaxies helps scientists map the universe and measure its vastness. The diversity of galaxies highlights the complexity and scale of the cosmos. Star formation is a fundamental process in the universe. Stars are born in giant clouds of gas and dust, forming clusters and galaxies. Studying star formation helps scientists understand the evolution of galaxies and the universe's structure. Observations of star-forming regions provide clues about cosmic distances and the universe's size. Planetary systems, like our solar system, are common throughout the universe. Each system contains planets, moons, and other objects orbiting a star. Studying planetary systems helps scientists understand the diversity of the cosmos and provides context for measuring cosmic distances. Exoplanets are planets orbiting stars outside our solar system. Thousands have been discovered, revealing the diversity of planetary systems. Studying exoplanets helps scientists understand the universe's complexity and provides new ways to measure cosmic distances. Cosmic evolution describes how the universe has changed over time. From the Big Bang to the formation of galaxies and stars, the universe has grown and evolved. Studying cosmic evolution helps scientists understand its size, structure, and future. The fate of the universe depends on its expansion and the influence of dark energy. Scientists debate whether the universe will continue expanding forever, slow down, or eventually collapse. Understanding the universe's fate helps refine measurements of its size and structure. Measuring the universe is challenging due to its vastness, complexity, and the limitations of our instruments. Scientists must account for cosmic expansion, dark matter, and dark energy. Ongoing research and technological advances help refine measurements, but uncertainties remain. These challenges drive innovation and deepen our understanding of the cosmos. Future technologies promise to improve our ability to measure the universe. New telescopes, satellites, and instruments will provide more accurate data, expanding our view of the cosmos. Advances in computing and data analysis will help scientists map the universe in greater detail, revealing new insights into its size and structure. Some theories suggest the universe may be infinite, extending beyond the observable region. If true, the universe's size is beyond measurement. Scientists continue to explore this possibility, seeking evidence through observations and theoretical models. The question of infinity challenges our understanding and inspires ongoing research. The multiverse hypothesis proposes that our universe is just one of many, each with its own laws and structure. While still speculative, this idea expands our perspective on the universe's size and complexity. Scientists explore the multiverse through theoretical physics and cosmology, seeking clues in cosmic observations. Scientists use a variety of methods to measure the universe, including parallax, standard candles, redshift, and cosmic surveys. Each technique contributes to our understanding of the universe's size and structure. Ongoing research and technological advances continue to refine these measurements, expanding our view of the cosmos. From our tiny vantage point on Earth, the universe's size is awe-inspiring. Our quest to measure and understand the cosmos reflects humanity's curiosity and ingenuity. The vastness of the universe challenges us, but also inspires wonder and exploration. Scientists continue to push the boundaries, seeking answers to the biggest questions. The universe is vast beyond imagination, shaped by cosmic expansion, mysterious forces, and billions of galaxies. Scientists use ingenious methods to measure its size, from parallax and standard candles to redshift and cosmic surveys. Our understanding continues to grow, driven by curiosity and technological advances. As we look to the future, the universe remains a source of wonder, inviting us to explore its mysteries and expand our knowledge. The search for alien life has fascinated humanity for centuries. Today, scientists use advanced technology and innovative methods to explore the universe for signs of life beyond Earth. From telescopes scanning distant planets to robotic missions exploring Mars, the quest is both scientific and deeply philosophical. In this video, we'll journey through the main approaches scientists use to search for extraterrestrial life, the discoveries made so far, and what these findings mean for our understanding of the cosmos. Let's begin by exploring why the search for alien life matters and how it shapes our perspective on the universe. Searching for alien life is more than just a scientific endeavor. It's a fundamental quest to understand our place in the universe. Scientists hope to answer profound questions. Are we alone? Is life common or rare? Discovering even the simplest forms of life elsewhere would revolutionize biology, chemistry, and philosophy. It could provide clues about how life originated on Earth and whether similar processes occur elsewhere. This motivation drives research across multiple disciplines, from astronomy to microbiology, and inspires international collaboration and investment in space exploration. Before scientists can search for alien life, they must define what life is. On Earth, life is characterized by growth, reproduction, response to stimuli, and metabolism. However, alien life might not follow these rules. Researchers consider the possibility of life forms based on different chemistries, such as silicon instead of carbon, or life thriving in extreme environments. This broad definition allows scientists to search for a wide range of possibilities, from microbes to intelligent civilizations. Astrobiology is the interdisciplinary science dedicated to studying life in the universe. It combines biology, chemistry, geology, and astronomy to investigate the origins, evolution, and distribution of life. Astrobiologists analyze conditions on other planets and moons, searching for environments that could support life. They also study extremophiles, organisms that thrive in harsh conditions on Earth, to understand how life might survive elsewhere. Astrobiology guides the search for alien life and shapes the missions sent to explore other worlds. Telescopes are essential tools in the search for alien life. Ground-based and space telescopes scan distant stars and planets, looking for signs of habitability. They analyze the light from exoplanets to detect atmospheric gases like oxygen, methane, and water vapor, potential indicators of life. Advanced telescopes, such as the James Webb Space Telescope, provide unprecedented detail, allowing scientists to study planets hundreds of light years away. These observations help identify promising targets for further exploration. Exoplanets are planets that orbit stars outside our solar system. Thousands have been discovered, many in the so-called habitable zone, where conditions might allow liquid water. Scientists study exoplanets' size, composition, and atmospheres to assess their potential for life. Some exoplanets show signs of clouds, weather, and even possible biosignatures. The discovery of exoplanets has expanded the search for alien life to the entire galaxy, offering countless possibilities. Spectroscopy is a technique that allows scientists to analyze the composition of distant planets' atmospheres. By studying how light interacts with gases, researchers can detect molecules like oxygen, carbon dioxide, and methane. These molecules may indicate biological activity. Spectroscopy is crucial for identifying planets with conditions similar to Earth and for searching for chemical signatures that could suggest life. It's a powerful tool in the ongoing hunt for alien life. Mars is a prime target in the search for alien life. Robotic missions like NASA's Perseverance rover explore the Martian surface, searching for signs of past or present life. These robots analyze soil, rocks, and atmosphere, looking for organic molecules and evidence of water. Mars missions have discovered ancient riverbeds, minerals formed in water, and complex organic compounds. While no definitive proof of life has been found, Mars remains a promising candidate. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, are considered top candidates for alien life. Both have icy surfaces and evidence of subsurface oceans. Scientists believe these oceans could harbor life protected from harsh radiation by thick ice. Missions like NASA's Europa Clipper aim to study these moons' environments, searching for organic molecules and signs of life. The discovery of water plumes on Enceladus has fueled excitement about the possibility of life in these hidden oceans. Biosignatures are chemical or physical signs that indicate the presence of life. Scientists search for biosignatures in planetary atmospheres, surfaces, and even meteorites. Examples include oxygen, methane, and complex organic molecules. The detection of biosignatures doesn't guarantee life, but it provides strong evidence and guides further investigation. The search for biosignatures is central to astrobiology and shapes the design of space missions and telescopes. SETI, the search for extraterrestrial intelligence, focuses on finding intelligent life by detecting signals from space. Scientists use radio telescopes to listen for patterns that could indicate communication from alien civilizations. SETI projects scan millions of frequencies, searching for signals that stand out from natural cosmic noise. While no confirmed signals have been found, SETI remains a vital part of the search for alien life, expanding our understanding of the universe. One of the most famous SETI discoveries is the WOW signal, detected in 1977. This strong, unexplained radio signal lasted for 72 seconds and has never been repeated. Scientists have analyzed the WOW signal for decades, but its origin remains a mystery. While it's not definitive proof of alien life, it highlights the challenges and excitement of searching for intelligent signals from space. The Drake equation is a mathematical formula used to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. It considers factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life developing. While the equation is based on many uncertainties, it helps guide scientific thinking and SETI research. The Drake equation remains a central concept in the search for alien life. The Fermi paradox asks why, given the vast number of stars and planets, we haven't found evidence of alien civilizations. Scientists propose many explanations, from the rarity of life to technological limitations or self-destruction. The paradox drives debate and research, encouraging scientists to refine their search methods and consider new possibilities. It's a reminder of the challenges and mysteries in the quest for alien life. On Earth, life thrives in extreme environments, deep oceans, hot springs, and frozen tundras. These extremophiles show that life can adapt to harsh conditions, expanding the possibilities for alien life. Scientists study these organisms to understand how life might survive on other planets or moons. Discoveries of extremophiles inspire new missions and guide the search for life in places previously thought inhospitable. Organic molecules, the building blocks of life, have been found in meteorites, comets, and interstellar clouds. These discoveries suggest that the ingredients for life are widespread in the universe. Scientists analyze these molecules to understand how life might originate elsewhere. The presence of organic compounds in space supports the idea that life could emerge in many environments, not just on Earth. Some meteorites found on Earth contain structures and compounds that resemble microbial life. While controversial, these findings spark debate about the possibility of life traveling between planets. Scientists use advanced microscopes and chemical analysis to study meteorites, searching for signs of ancient microbes. The discovery of potential microbial evidence in meteorites would have profound implications for the origin and spread of life. The panspermia hypothesis suggests that life could spread between planets via comets, asteroids, or meteorites. Scientists explore whether microbes can survive space, travel, and impact. Experiments show that some bacteria can endure harsh conditions, supporting the possibility of panspermia. This idea expands the search for alien life, considering not just local origins but cosmic journeys. Chemistry is central to the search for alien life. Scientists study chemical reactions that could produce life's building blocks, such as amino acids and nucleotides. They analyze planetary environments for conditions that support these reactions. Chemistry guides the search for biosignatures and helps interpret data from telescopes and robotic missions. Understanding chemistry is key to recognizing alien life, even if it's very different from life on Earth. Scientists use habitability criteria to assess whether a planet or moon could support life. Key factors include the presence of liquid water, a stable atmosphere, and suitable temperatures. Researchers also consider energy sources, such as sunlight or chemical reactions. These criteria help prioritize targets for exploration and guide the design of missions and instruments. Water is essential for life as we know it. Scientists search for planets and moons with evidence of liquid water, ice, or water vapor. The discovery of water increases the chances of finding life and guides mission planning. Water has been found on Mars, Europa, Enceladus, and many exoplanets. Its presence is a key indicator of habitability and a focus of ongoing research. Analyzing planetary atmospheres is vital for detecting signs of life. Scientists use telescopes and spacecraft to measure gases like oxygen, methane, and carbon dioxide. These gases can be produced by biological or geological processes. Comparing atmospheric data helps distinguish between natural and potential biological sources. Atmospheric analysis is a cornerstone of the search for alien life. Advanced technology enables scientists to search for alien life in ways never before possible. Powerful telescopes, robotic explorers, and sophisticated instruments collect and analyze data from distant worlds. Technology allows researchers to detect faint signals, study tiny molecules, and simulate alien environments in laboratories. Continued innovation is essential for expanding the search and making new discoveries. Scientists simulate alien environments in laboratories to test how life might survive elsewhere. They recreate conditions found on Mars, Europa, and other worlds, exposing microbes to extreme temperatures, radiation, and chemical mixtures. These experiments reveal the limits of life and help interpret data from space missions. Simulating alien environments is a crucial step in preparing for future discoveries. The search for alien life faces many challenges. Distant planets are hard to reach and study, signals can be faint or ambiguous, and distinguishing biological from non-biological processes is complex. Scientists must overcome technical, financial, and philosophical obstacles. Despite these challenges, the quest continues, driven by curiosity and the hope of groundbreaking discoveries. Some discoveries in the search for alien life are ambiguous. For example, methane detected on Mars could be produced by microbes or geological processes. Organic molecules found in meteorites might be contamination or evidence of life. Scientists use rigorous methods to rule out false positives and confirm findings. Ambiguous discoveries highlight the need for careful analysis and ongoing research. False positives are a major concern in the search for alien life. Signals or chemical signatures may appear promising, but turn out to be natural phenomena. Scientists use multiple methods and independent verification to confirm discoveries. Peer review and collaboration help ensure that findings are reliable. The process of verification is essential for building trust in scientific results. The search for alien life is a global effort. Scientists from around the world collaborate on missions, share data, and develop new technologies. International partnerships enable larger, more ambitious projects and foster a sense of unity in the quest for discovery. Collaboration increases the chances of success and ensures that findings benefit all humanity. Space missions and probes are vital for exploring planets and moons firsthand. Robotic explorers collect samples, analyze environments, and send data back to Earth. Missions like Mars rovers, Europa Clipper, and Voyager probes expand our knowledge and search for signs of life. Each mission brings new discoveries and challenges, advancing the quest for alien life. Sample return missions bring material from other planets or moons back to Earth for detailed analysis. These missions allow scientists to study soil, rocks, and atmospheric samples with advanced laboratory equipment. Sample return missions are planned for Mars and other targets, offering the best chance to find definitive evidence of alien life. Future missions will use even more advanced technology to search for alien life. Planned projects include new telescopes, robotic explorers, and sample return missions. Scientists hope to explore ocean worlds, study exoplanet atmospheres, and search for biosignatures with greater precision. Continued innovation will expand the search and increase the chances of discovery. Artificial intelligence, AI, helps scientists analyze vast amounts of data from telescopes and space missions. AI can detect patterns, identify anomalies, and prioritize targets for exploration. Machine learning algorithms improve the efficiency and accuracy of the search for alien life. AI is becoming an indispensable tool in modern astrobiology. Citizen science projects invite the public to participate in the search for alien life. Volunteers help analyze data, identify signals, and support research. Projects like SETI at Home use distributed computing to scan radio signals for signs of intelligence. Public involvement increases awareness, enthusiasm, and the pace of discovery. The search for alien life raises important ethical questions. How should we respond if we find life? What are the risks of contamination? Scientists develop protocols to protect both Earth and other worlds from biological contamination. Ethical considerations guide mission planning and international agreements, ensuring responsible exploration. Planetary protection protocols are designed to prevent biological contamination during space missions. These protocols ensure that spacecraft are sterilized and that samples are handled safely. Protecting both Earth and other worlds is essential for preserving scientific integrity and preventing unintended consequences. Planetary protection is a key aspect of responsible exploration. So far, scientists have found many intriguing clues, but no definitive evidence of alien life. Discoveries include organic molecules, water on Mars and icy moons, ambiguous signals, and extremophiles on Earth. Each finding advances our understanding and guides future research. The search continues, with new missions and technologies offering hope for groundbreaking discoveries. Ambiguous signals, such as the WOW signal and unexplained methane on Mars, keep scientists searching for answers. These findings are not proof of alien life, but suggest that the universe is full of mysteries. Careful analysis and continued research are needed to interpret ambiguous evidence and distinguish between natural and biological sources. Despite decades of research, scientists have not found definitive proof of alien life. The search is ongoing, with each discovery raising new questions and possibilities. The absence of proof does not mean life is impossible, it simply reflects the challenges and complexity of the quest. Scientists remain optimistic and continue to explore new frontiers. The search for alien life has a profound impact on science and society. It drives technological innovation, inspires education, and encourages philosophical reflection. Discoveries in astrobiology influence fields from biology to engineering and shape our understanding of the universe. The quest for alien life unites people across cultures and generations. The search for alien life raises deep philosophical questions about existence, uniqueness, and the nature of life. If we find life elsewhere, it could change our perspective on humanity and our place in the cosmos. Philosophical implications drive debate and inspire new ways of thinking about science, ethics, and society. The future of the search for alien life is bright. New missions, technologies, and international collaborations promise exciting discoveries. Scientists will continue to explore planets, moons, and exoplanets, searching for biosignatures and signals. The quest is ongoing, with each step bringing us closer to answering the age-old question, are we alone? Scientists remain hopeful that the search for alien life will yield groundbreaking discoveries. Each mission, experiment, and observation brings new knowledge and possibilities. The universe is vast, and the potential for life is immense. Hope drives research, inspires innovation, and keeps the quest alive. To summarize, scientists have found organic molecules, water, ambiguous signals, and extremophiles, but no definitive proof of alien life. The search is guided by astrobiology, technology, and international collaboration. Each discovery advances our understanding and shapes future research. The quest for alien life is one of the most exciting and important scientific endeavors. The search for alien life is far from over. Scientists will continue to explore, analyze, and innovate, driven by curiosity and the desire to understand the universe. Each new mission and discovery brings us closer to answering fundamental questions about life, existence, and our place in the cosmos. The quest continues, inspiring generations to look to the stars. In conclusion, the search for alien life is a journey of discovery, innovation, and wonder. Scientists use a wide range of methods, from telescopes to robotic missions, to explore the universe for signs of life. While definitive proof remains elusive, the quest has transformed science and society. The search for alien life will continue, shaping our understanding of the cosmos and inspiring future generations.